Hello, everyone. This is Aniakin. Yes, that's Aniakin. If you're new to our channel, welcome. If you are returning and or a subscriber, we appreciate you. Welcome back.
Hi everyone, I'm Ava. Yes, this Ava, and you are watching episode 3 of our coverage of Domain 1 Data Preparation for Machine Learning to help you prepare for the AWS Machine Learning Engineer Associate exam.
That is correct. Thank you for that, Ava. And in episode 1, we did an overview of data processing. In episode 2, we dove into data collection and ingestion. Today, in episode 3, we're unpacking data pre-processing, a crucial step before you feed data into your model.
That's right, Aniakan. You can think of pre-processing like tuning the engine of a car before a road trip. It makes sure everything runs smoothly when you hit the highway. In our case, it's the highway of machine learning.
I love it. That's my kind of highway.
Nice.
All right. Okay. Yeah. Next thing is data cleaning. Data cleaning, that is the process of fixing or removing incorrect, corrupted, or incomplete records, like proofreading a manuscript before you publish, or Ava checking the tire pressure on her car before going on a long road trip.
Nice. So what happens if our dataset has missing entries, Aniakan?
Great question, Ava. As you know, real world data often has gaps. In episode 1, we called it messy data, right? And so there are three main options that we'll talk about today. So one is replacement with constant values, also known as constant imputation. And this is where you fill missing spots with a fixed placeholder, something that wouldn't appear under normal circumstances in the data. And for numerical values, we might use something like zeros or large, or maybe something like 999, anything that would not normally appear in the data in the case of numerical values. For categorical data, we might use something like unknown or not applicable. And it's like a good analogy would be like filling out a form where, let's say, you don't know one of the fields, one of the entries for the field, like the city. So you write NA. You're using a standard placeholder to indicate missing information in a way that allows that form to still be processed. And you'd use this when the fact that something is missing carries its own meaning.
Yeah, right. That's a good one there. We also have statistical imputation, and this has to do with the mean or the median. And what it is it's computing one of these simple statistics. The method works for numerical data only, and is going to assume that the missing values are random. Just a quick refresher if you don't remember this, but the mean versus the median. The mean is the normal average and the median is the midpoint when you sort all the values. And maybe to offer an analogy here, it's like estimating the typical temperature for missing recordings in a weather data set by using the average of the known temperatures for that time of the year.
Nice. And we also have predictive imputation. And this is where you train a predictive model like KNN, K nearest neighbor, or a regression to estimate missing values based on other features. And analogy here would be if you know someone's height and weight and not their shoe size, you could look at people around them or other people with similar weight and height to predict the shoe size.
Yes, and then after handling the missing values, we also need to catch outliers and duplicates, right?
That's right. Exactly right. Outliers or extreme values that can mislead your model, and duplicate or repeated records that can bias results. And we can use one of several methods to detect outliers, including outlier detection, right? Outlier detection, and that includes methods like the z-score method or simply the average distance method. And you'd use this to find, let's see, you'd use this to take a look and find how far each value is from the average, right? Say 3 standard deviations from the mean, like, how far is it from the average? If it's really far, right, like 3 times further than the normal, then it might be an outlier. Another method is IQR method or the range method. So this looks at the middle 50% of your data. And if something falls away from that, far away from that, outside that middle range, right, it might be an outlier. And the third method is visualization, or maybe just, visual check. And this is where you represent your data using simple charts like box plots or histograms. And with visualization, with visual checks, anomalies or unusual values can stick out visually.
Oh, yeah, that is very helpful to know about. By the way, can I offer an example of an outlier from my area of the Pacific Northwest here in Yekan?
Yes, please.
Okay, so Bill Gates is mentioned. It's valued something like over $180 million, and it's an example of an outlier because its price drastically deviates from the typical home values in Medina, Washington. So if we are to look at the mean, for example, it will be significantly pulled upward due to the extreme value. On the other hand, the median remains relatively stable since it only considers the middle value. So as a side note here, folks, the median is often the preferred over mean when analyzing housing prices, as it is, as you can see, more resistant to the influence of extreme outliers.
I love that. And I just noticed that Medina and median are anagrams of one another. So that's
Wow.
another bonus. All
Bonus
right.
catch. I didn't catch that. Well, nice one, Aniakan.
Yeah, very cool. All right, and the other method is, the other thing we want to do with the data is remove duplicates, right? Um, Duplicate rows can skew your model towards patterns that appear too often. And sometimes, usually, we don't want that. So Amazon SageMaker, for example, can handle this. Or we can do it programmatically, right? There are functions like the drop duplicate functions in both Python pandas and Spark data frames. All right. Oh, and a useful analogy here with respect to duplicates removal is, let's say you accidentally send multiple invitations to the same email address. You don't want that. One invite per person, please. Okay. Next, we want to take a look back at the another feature, right? So let's say at this point your data is clean, right? You've cleaned your data, you collected and cleansed your data, and so now we have this big, beautiful data set. Okay, now the question becomes, what's next? Do we use it all to train our model?
Yeah, that is a great question, Aniakan. So I think you're referring to data partitioning here. And with this step, what we're going to do is split the data set into training, test, and in some cases also validation sets. And so imagine you're studying for an exam, right? So the training set is going to be your practice questions. The validation set is like the mock test that you can take and then tweak your study strategy. And finally, the test set is going to be the final exam. There are some examples, not a hard rule, but for example, you can split the data, let's say 70% for training, 15% validation, and 15 for testing. Some scenarios might just use train and test. For example, that's common in cross-validation. And then different split ratios may be appropriate based on the different data sets as well, the size of the data set, I should say.
Yep, very cool. And speaking of cross-validation, that's a good one to know for the exam. And it is a resampling technique, especially useful if you have limited data. And a common type of cross-validation is k-fold cross-validation. And it works like this, right? You start with the full data set and you split that into equal parts. And you'll typically see 5 or 10 parts. So you typically see the K being 5 or the K being 10. Then in turn, we have those um, data, the parts of the data. You split that up, and most of the data used to train the model, like 4 parts of the data is used to train the model, and you reserve one of those parts to test the model. And then you go through each iteration and you pick different of those 5 parts to do the testing, while the other ones, the other parts are used to train the model. So you repeat that until all parts have been used for testing once. And then the final performance is averaged across all of the different iterations, in this case, all 5 iterations. And so why do we do this? It helps make sure that your model works well with different kinds of data. And it's especially useful when you don't have, like I mentioned earlier, lots of data to work with. By the way, Ava, how does AWS help with data partitioning?
Yeah, so SageMaker has a built-in functionality that is going to help to partition data right inside SageMaker Studio, so you don't have to write any custom code for splits here. SageMaker is going to be a tool I'm going to be mentioning a lot, and you too probably, because it solves
Yes,
a lot of these problems along the way
yes,
here.
yeah.
Okay, great. And so next we also have scaling. Before the models can see the data, so as numbers, right? Maybe heights or prices, they need all features to be on the same scale. And so no single feature dominates just because the values are larger.
Mhm.
And what kind of we have a process here. What is that process, Aniakan?
Yeah, absolutely. Yeah, the process is the scaling process. So if you need to scale, right, you would typically go through a two-step process. That is, before you actually do the scaling, we check to see if there's a pre-scaling step that is needed, such as handling outliers or converting units, see whether or not that's needed. With respect to unit conversion, we make sure that every feature uses the same unit. An example might be you have uh, data, some of which is expressed in kilometers and the others of which are expressed in meters. We don't want that. We want them to use to use the same scale. So you convert in this case you might convert kilometers to meters. And we do this because algorithms expect to see data that does not have any unit metadata associated with it. So we convert all to one unit, and then we can get rid of the unit metadata itself. And next, once we're done any pre-scaling step that is needed, we then can start with the scaling process. And this brings every feature into a comparable numeric range. And there are two scaling methods that we'll take a look at. One is normalization, the other one is um, scaling. I'm sorry, standardization. So
Standardization.
with normalization or the min-max scaling, we squash values into a fixed range, typically between 0 and 1. And let's say, for example, you have many songs, and these songs are playing at different volumes. You normalize them so that the quietest song is at 0 and the loudest one is at 1. Then everything else, every other song scales proportionately between those two values. And you'd use this typically with distance-based algorithms like K nearest neighbor, and many neural networks. And this topic is a good one for the exam. So know, for example, like I just said, that min-max scaling transforms each feature's values to fall between 0 and 1, where the minimum value becomes a 0 and the maximum value becomes a 1, and all other values are proportionally scaled between those two values.
Great. Yeah. And we also have what else? Standardization. I think you mentioned that, Aniakan.
Mhm.
Also known as Z-score scaling would be one. So what it does is it centers data around 0 by subtracting the mean from the value and then dividing by the standard deviation. And let me give you an analogy that might sound a little more easy to understand than what I just said here, if you're not a statistics person necessarily. So when your teacher, let's say, transforms a raw test score into how many points above or below the class average you are, then the score at average is going to become like the 0. And you're going to use this type of technique for algorithms assuming normally distributed data, right? You know, the normal distribution. So linear or logistic regression algorithms, you can use this type of technique there.
Nice. And I bet this is supported in SageMaker, right, Eva?
Oh, you know it. The answer is yes. In SageMaker Studio, Data Wrangler, we actually saw a demo of that in a previous episode, offers a point and click transforms for both min, max, and z-score standardization. And they're also complete before and after histogram, so you can visually see the effect as well.
Nice. Love it. All right. So next we talk about unbiasing and balancing the data. So how do we handle data bias and how do we handle in bias in our data sets? So bias and imbalance, that's when some groups or classes in your data are overrepresented or underrepresented, which can make models unfair or inaccurate.
Yeah, that's right, Aniakan. So first, how do you handle this kind of situation? First, you need to detect the imbalance, and this can be done by using charts like histograms or pie charts. It's like checking that both teams have the same number of players on the field, right? I don't know,
Mhm.
I like soccer a little bit, and sometimes when one player needs to be, or football, I guess depends where you come from. When one player maybe is given a yellow card and they need to leave, then we have an imbalance on the field, right?
Love
And
it.
so also there are bias metrics as well that you can use, and we will actually see those in an upcoming demo. Then of course you need to mitigate the problem, the imbalance in this case, and there are a couple of techniques to mention here. So we have the idea of oversampling. SMOTI is one example, synthetic minority oversampling technique, which creates synthetic examples of the minority class. Duplication is going to be simply repeating the existing minority samples, and then the opposite is going to be undersampling, where you actually delete the excess majority sample, again with the idea of balancing, or you can just do a random sampling where you pick a subset to reduce the dominance.
Mm, nice. And then there's class weighting. So this assigns higher importance or weights to minority classes during model training. For example, instead of changing the data itself, class weighting modifies how each class influences the model's learning. An analogy might be, you give certain players more voting power in team decisions to ensure that their voices are equally heard. And this is another good exam tip, right? So class weighting is useful when you want to keep all original data. However, you need to balance model sensitivity.
Yeah, and in
All right,
fact, yeah.
it's uh, it's time for demo, right, Ava?
Yes, Riek, and it's demo time. So how about we look at the demo of bias
Yeah,
detection with the SageMaker Clarify service, or
sounds
feature, I
great.
should say. So let me add myself to the screen here. Okay, please let me know if you can see my screen okay.
I can, yes.
Great. All right, folks. So in this demo, we're going to use the SageMaker to clarify. And I'm starting here on the Clarify homepage on AWS. And so you can use Clarify to evaluate models and explain predictions. But also, as you see, you can use it for detecting bias in data. So SageMaker Clarify shows up on the exam, definitely, and some of its features are it can evaluate foundation models. It's used for compliance here as well, and it has produces various accessible, metrics and reports again for compliance. So you can evaluate foundation models. Maybe we'll come back to that in an upcoming uh, lecture that we have and video recording. But today we're focusing on detecting bias, and that's what we're going to do with SageMaker Clarify. And you can use Clarify from the console or from the from programmatically as well. So
Mm.
for this demo, I'm going to work with a bank marketing data set, and it is used for direct marketing campaigns with phone calls. And the goal is going to be to predict if the client will subscribe to a term deposit, which is a yes or no. Okay, so with this little background in mind, let's go over to this is a Jupyter notebook. So if you're not
Mm.
familiar with those, they're interactive way to run Python. And so I'm going to start here. So again, this is programmatically working with SageMaker Clarify.
So yeah, that's a good question, Eva. So you're doing this in the notebook, which allows you to programmatically go through the process of, in this case, what we're detecting bias. But we can we do this also through the console if we wanted to?
That's a great question, and you absolutely can. So you can do this through the console, like with any other service, but also you can do it programmatically, and that's what I'm going to show you here, right?
Nice.
Um, Great. Yeah. So in this case, I'm going to focus particularly on the parts that have to do with Clarify here, not go through the entire example necessarily. But here I'm going to import from the SageMaker Clarify package, the bias module. I'm going to import a function called report, and that is going to really easily render this data bias report for us. So that's the first thing to do here, to point out, I should say. And then I'm going to load the marketing data set I showed you into a data frame. So make it columnar, rows and columns, so that it's available for my notebook and for my environment. And then you can use, data pandas commands like columns and here to just analyze your data a little bit, look at what columns are available. I can look at the first 5 rows in this case.
Mm.
And this
I
is
can
just
see
kind of,
that. Sorry, I was
oh
just going
yeah,
to say I can see that doing it programmatically gives us a lot of flexibility and ability to customize it, perhaps even more than we can through the console. But yes, there's I can
yeah.
see the value in doing this programmatically via the SageMaker notebooks.
Yeah, that's a great point, and yeah, I can absolutely 100% agree with you on this one.
Okay.
Great. And so after you have kind of become familiar with the data, now the next step here is going to run a visualization, just like Aniek mentioned earlier. This is going to be a pair plot, which is basically several scatter plots that are going to examine the relationship between variables. And there is a lot going on here. I'm just going to zero in on this one, which is a scatter plot of the campaign and the age.
Mm.
And you can see the age begins, like, let's say with 0, but 25 goes up to 100, and this is the numbers of the campaign. And just visually speaking, what I'm noticing here is a lot more calls were made up to, let's say, I don't know, this maybe
Mm.
55 or 60, right? Do you see any egg,
Yeah,
and it's kind of
yeah,
falling off there?
falls off. Yeah.
Yeah.
So this is great. We're seeing this information visually. It gives us a good high level, big picture of what's going on. Is there a way that we can actually drill down though into the numbers
Yeah,
in notebooks?
that's exactly right. This is giving us a good sense, but it's maybe not sufficient. So we want to actually get to those metrics, and that's what we're going to do next. Great point.
Nice.
Great. We just have a small interesting bookkeeping detail here, which is that the age data is continuous, right? And what we need to do is we need to split it into bins, categories. And so this is what is happening on this line right here. Basically, instead of having a continuous age, we're going to split it into a bin of the young age, middle age, and old age. So 3 bins. And then we're going to be actually looking at this any imbalance in terms of the age discrimination, and that's referred to as the facet here. So this is what we're going to look for in those metrics. And then the next thing here, so just one line, folks, from SageMaker Clarify is going to allow us to produce this report to look at all these different metrics that have to do with bias. And what is interesting is this also allows for controlling for education. So this is also known as the confounding variable here. So even if education is accounted for, do we still see any biases here? And this is the result. So when I run this cell here, this is the result, and it's a lot. And don't worry about all of it, but I'll highlight just a couple of things here. So let's look at those bins that we saw that we created upstairs. So is the actually so it starts with the middle. There's the first bin, and then these are all the metrics that have to do with the middle age bin. Then we have the young bin, and here are all the metrics that have to do with the young bin. And finally, we have the old age, and here are all the metrics that have to do with old age. And we don't necessarily maybe want to look at each one of them right now, but just as a case in point here of the idea, I'm going to, well, let me backtrack for a moment. For the exam, you want to be familiar with as many of those metrics as you can. But just for this demo, I'm going to focus on a couple. I'm going to focus on the class imbalance here and on the difference in positive proportions in labels. So this is the metric, and this is its value. And so for the class imbalance, a metric of 0.98 shows strong class imbalance. And again, this is for the old group. Looking at the DPL metric here, it's negative 3.8. And this is an indication for this metric. What it means is we have a large difference in positive prediction rates. So to summarize kind of the finding here, this suggests that the model treats the old age groups significantly differently compared to other age groups such as the young and the middle that have relatively lower bias metrics, even when accounting for education.
All right, very cool. So we've detected detected the problem, the bias.
Yes.
What's the mitigation techniques?
Yeah, that's a very important question. I'm glad you brought it up, Onyeka. We have several different techniques at our disposal. One of them is going to be resampling, where you balance the data set using over and under sampling from the old group. We have this weighted loss that you talked about. You apply class weights during training to give a more importance to the underrepresented groups. And also we have, you can generate synthetic data for the old group using techniques such as
Nice,
SMOTI. Yeah. Yeah.
cool.
So that's all I have for this demo. Hope you found it informative.
Yes, I very good. I really appreciate that. A great demo and great highlight of some of the things that we need to focus on for the exam. Well
Yeah,
done
absolutely.
as always. Okay, so yeah, let's keep going. We're
Let's
all
keep going.
next section is a conversation around
Data
augmentation.
augmentation. Yeah, that's right.
Yes,
Exactly.
yeah,
So data augmentation, this is going to be artificially expanding your data set so your model gets more practice, so to speak, examples and becomes more robust.
exactly. And we can look at techniques like uh, Ava mentioned synthetic data generation and image augmentation, right? Synthetic data generation algorithmically,
Good job with
say
this
that
hard
one
one.
time fast,
Not easy.
where you create new records from scratch. And image augmentation, you apply, rotations, crops, flips to existing images. It's like looking at an object from multiple different angles. AWS even offers built-in augmentation pipelines in SageMaker for both images and text data, so you can automate those transformations.
Yeah, how cool is that? So, Anieka, I think we covered a lot of ground today. And folks, this is all on the exam. So hopefully you're going to find it helpful. But maybe let's do a recap here of
Yes,
everything we talked about. So I'm going to start by, let's say, with data cleaning. So you need to handle missing values with constant replacement, statistical or model driven. And you need to also detect outliers and duplicates.
love it. And we also talked about data partitioning, where we split data, the full data set, into training, test, and usually and sometimes validation sets.
Yeah, that's right. We also talked about scaling techniques where you convert units, then normalize between 0 and 1, or you standardize, which are the zero-centered features.
Mhm. And we covered bias and imbalance. Uh, we want to detect skew and mitigate them with oversampling. They've also talked about undersampling and also class weighting.
Yeah, that's right, Aniakan. And also data augmentation, to circle back to this, expand data sets with synthetic data or transformations. And again, SageMaker pipelines is going to make that easy.
All right, very cool. So, folks, that is it. That's it for episode 3. Next time, in episode 4, we'll dive into feature engineering, where we transform and combine cleaned data into the most informative inputs for our models. You won't want to miss it.
That's right. See you in episode 4, folks. And don't forget to like and subscribe. Thanks, everyone. Until next time.